There. Sorry about that. So the if a child set the file descriptor to be an O non-block, then the parent would also see it as O non-block. And if it didn't really anticipate that, you could get all sorts of funs, because it would start seeing E again. E would block errors. A classic symptom in that we use to see in OpenBSD is you'd have a threaded program die, so it couldn't reset the file descriptor state. And then you'd try to fire up VI or something, and VI would instantly exit, because it would try to read, get an E again from the terminal, and exit. It looks like you did end a file. So it was really kind of annoying, and we put in various workarounds at various times, but they were just workarounds. In the end, you can't solve that problem with that particular tool. Of course, the non-blocking, O non-block doesn't let you do everything non-blocking, really. There's absolutely no way for you to do a non-blocking open of a FIFO in the file system. If you try to do it, it'll return an error, but you can't then poll for when you would actually succeed, which kind of defeats the whole purpose of that whole process. You also have to deal with things like kevent and socket timeouts. We eventually did put in code to deal with socket timeouts, but it meant that you had lots and lots of system calls just to check to see, oh, look, did I put a set of socket timeout on this thing? And some things would go ahead and block even though you didn't want them to be blocking. Disk I/O will block no matter what you say. If your NFS server is down, other threads will not get to run. So at some point it said, okay, everyone knows the right answer. The right answer is you go ahead and teach the kernel about threads. So what we called this was RThreads. Standard one-to-one architecture. Every single thread in Userspace is a thread in the kernel as well. This minimizes the amount of changes. You don't have to have the vast complexity of a thread scheduler in Userspace or anything like that. You can just let the kernel deal with it. Indeed, many of the other operating systems that did go the so-called end-to-M method have now since then said, this is too much work. Let's all go to one-to-one. Solaris did that, for instance. In Solaris 8, they made it optional. In Solaris 9, it's the only way to do it. FreeBSD, I believe you guys did that as well. Yep. So for OpenBSD, the first initial effort was just minimal changes. Okay, we'd just stick a struct process above the struct proc. So struct proc remains the schedulable entity, the thing that actually is the thread level. And just a handful of system calls to actually pull this off. rfork, which existed for kind of stolen from Plan 9, a new flag, RFthread, was added to say, create this as a thread inside the process. You have to have a way to say, just kill one thread. Exit continues to take down the entire process. And then you need some way to identify what thread this guy is. And sigdivert is a way to handle the sigwait system call in POSIX. This is a way for one thread to steal signals from the process. And finally, you need some way to have the threads actually go to sleep and wake each other up. And for OpenBSD, this was basically an export of the kernel's tsleep and wakeup primitives to Userspace, where you pass an identifier as a rendezvous point. And actually, digging up for this paper, I discovered that Ted actually presented this here at EuroBSDcon back 7 years ago. So, why he did it? Yes, it was purely for excellent that. Yeah. Yeah, so the first implementation solved that problem, but it didn't work for anything else. Well, yeah. So as Henny's saying that the original one was just to make it so XMMS, the audio player, would actually not skip when you were dealing with the playlist and stuff. Honestly, that was my first use of it too. And it turns out we've actually solved that problem now. Their sound system is so much better now that that's rarely a problem even now. So a bunch of things were not right about that. The minimal implementation was exactly that, minimal, and created all sorts of fun problems because it wasn't doing things the way you'd expect. Some of you may have flashbacks of this diagram from your Unix courses. This is the rough diagram of the kernel's data structures for processes and process groups. That's the P group there. session structures, the TTY, showing how all the connections between them as they point out, okay, who's my sibling, the chains and lists of stuff. So one of the things we had to change is to fix this all up, because these were all done with the initial implementation. It was the threads were actually still chained together as siblings. This meant things like a thread would fork and another thread would try to wait for the child of the first thread, and it couldn't do it because it wasn't on that thread's children list. Okay, that's just wrong. Okay, so we have to move that around, have to move that stuff up to the process structure. Set PGID actually lets you put different threads in different process groups, which, yeah, job control was a little hosed if you tried to pull off some of that stuff. So we tried various times to just do parts of this, okay? We made us try, okay, can I just move the children bits and the parent pointers around? Okay, no, that doesn't work. How about if I move the process group session stuff and leave the children stuff? No, it turns out these things are just so bad, totally related to each other, that you just have to move them all at once. You just have to go through and say, okay, change all this stuff to proc, from proc to process, change all this stuff, and, you know, move these members around. It just has to be one big change. There was spent most of one of our hackathons in Edmonton doing this, and we committed the week after, and it actually worked on the first try, which was wonderful. One interesting note about this is that there's things like one of the security checks in set PGID to change your process group is that you're allowed to change the process group of a process which is one of your descendants. So you have to walk how it does this, how the kernel checks this, is it actually starts with the one process, the supposed descendant, and it just walks the parent pointers up until it finds you know, either it runs into this process we're doing the test for, or it runs into init. Okay, it's an assumption here, you know, the process tree, it's a directed acyclic graph. So that's an example of some place where you have to be doing these sorts of interrelations between the process tree and the process group kind of stuff. That one had a bug in it, though, interestingly. Get back to that. So one of the things, sigacts in the kernel side, so this is where all the signal information is stored in the everything that you do with sig action stuffed here. So the handler, whether it's ignored or not, is SA info set, all that kind of bits. That's actually was already shared. We actually had that shared because it was in a separate data structure, which there was a common reference count for it. But the information about what signals, there was caches of some of this stuff. There was p_bar sigignore was basically just a bit set of all the signals that this process was ignoring. The problem is that this was stuck in the proc structure, so you could actually, if you created some threads and then change your signal disposition, you could have different threads having different conceptions of which signals are being ignored. So that's not very easy, so we had to move that stuff all up to the struct sigacts. And then NFS caught fire. This picture on the right is actually Bob Beck, Theo, Thib, and myself reading the NFS call graph. So. Delayed writes, when you do a write, it can be left pending, waiting for some other stuff until the NFS decides it needs to flush it out. It carries a pointer in the UIO structure inside of it, even if it's a delayed write. And there was nothing to keep the process from going ahead and exiting. So we were actually having this pointer to a dangling process, and if someone hit a Control-C at the right point, then the sig_inter code that says, okay, you can interrupt NFS writes would actually be looking at this dangling proc. This was a bug before, we just never knew it because the pointers were not actually, they were still mapped in the kernel space. So it was a dereference of of a freed pointer, and just, you got away with it. But now, with the moving of this cache information into sigacts, now it has to do another dereference, which at this point had been overwritten as part of the free process, and so we started seeing panics. And so we actually had to back it out, track this down, stare at the NFS call graph, rip the pieces of our hair out, and then find the right places that they know. If you're doing a delayed write, you don't actually care about the process that actually started it anymore. Chop that off, set it to null. You can't interrupt those anymore, and off you go. So that did go in. Just took some hair. Other example things, there's kevent. There's one of the filters in kevent lets you monitor processes. So you can say, I want to watch, exits, forks, that sort of thing. except it was watching threads actually, so, and you didn't have any way to know which was a thread and what was a process. Easy to fix. The only trick there is that we were actually using that in our thread library to detect when a thread had gone away. One of the tricky parts of thread libraries is at some point you want to free a thread's stack. So how do you know when it's safe to free the stack? Okay, that thread on its way out can turn off the light or something, but it still has to make that system call to go away. So it's pushing some stuff onto the stack right then. So you need to do something from inside the kernel to let everyone else know, okay, yes, the thread's gone, it stopped using its stack, you can free it, you can do whatever you want to it. So we'd been using kevent by sending a kevent evfiltproc to say, watch the thread. But that couldn't, with the fix to how we wanted kevent to work, we couldn't do that. So we had to change it to use threxit. The exit to kill the thread thing now actually sets a flag for you in Userspace as a copy out. That's actually stole that idea. One of the great things about doing that OpenBSD by being one of the last groups to do this is that we get to steal great ideas from all the rest of you. So that was taken a bit from the Linux clone stuff. There's a thing where there's a flag where it says zero out the TID. Okay, so you pass that in. Same sort of idea. Ktrace. Ktrace had there's some fun bits in it in order to dealing with credentials of what credentials should be writing ktrace records as. But I mainly wanted to mention this so I could thank whoever was the smart cookie at FreeBSD who said, let's write structures too. Because that really made life a lot better and easier to debug things. When you actually, instead of just seeing, oh look, this function was being called, system call had this nice pointer argument. Okay, great, cool. What was it pointing at? But you could actually have it dump the actual structure information, entire values, and you could say, oh, we were passing in something completely bogus. And it's proved very useful for debugging, helping, working with our ports group to debug third-party stuff, where when you're lost in a maze of C++ code, and you can't figure out where the hell that call is coming from, you can at least get what the arguments in the structure was. We've actually run with this quite a bit. Otto Morbik, I probably mismangled his name, with OpenBSD is adding lots of flag decoding, and it's much nicer now. Resource limits, usages, you really want these accumulated, and I actually didn't think this was that important, and then SB started throwing things at me. When back in February, we finally made the switch and said, okay, that's it, we're turning the libp thread is no longer the old user space, it's now the new one, bump all the version numbers, blah, 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 blah. And they said, well, hey, the resource usage information is all wrong and it's screwing up DPB. Or those who attended the talk yesterday learned how the ports build stuff, automation, now by measuring usages can schedule the order of the ports down to the point where they all finish in 5 seconds on 8 different machines. So they needed that accurate usage information so they could estimate and place and schedule things in the right order. So by doing that, they made me put that further up in the list and fix it. And it is useful to know, for instance, when that one thread in Firefox is spinning. So. Not that it ever happens, so yeah. Yeah, exactly. One of the eviler things that you have to do as you work with the threads in the kernel is that there's certain operations which just have to be single-threaded. If not, you'll pull your hair out. Execv, for instance, is defined as when it succeeds, there's only one thread in the process after that. So all the other threads have to be hauled out and shot somehow. And you need to do that at a safe point, because you really want to make sure that they can't, as their last operation, do a copy out or something in the new process's space and trash its thing. So it's based on ideas from FreeBSD, set up a couple things and some functions for basically catching setting some flags in the process structure that processes check on entry to the kernel and then whenever they go to sleep so that they can know, okay, instead of going to sleep, I'm going to bail all the way out, stop and die or suspend or whatever. You also have to do this for core dumping. This is actually one of the things that got me involved in RThreads was I was working with RThreads in XMMS and discovered that if XMMS core dumped, sometimes your machine would panic. Because the core dump code in the kernel would walk the thread list, see, okay, how many ELF notes about registers for processes I need to write, and then it would actually walk the list again and actually write them out. And sometimes one of the threads would go away in the process of that, and an assertion to say, did I get the same count both times would fail. So you have to really lock those all down, say, no, here's the actual set to go. So thank you, FreeBSD. ptrace, this was one of the last things we actually got right, mainly because ptrace is really complicated. By the way, I don't know how many people know this, but ptrace, when GDB, for instance, you attach to a process, it actually, in the kernel, does so by, the kernel reparents the process, the target process. So if I'm debugging, ls or something, that ls process, instead of being a child of the shell that I started on, perhaps, becomes a child of GDB. Okay, so that's how it then gets all the events, and it can do wait. It can actually wait for the events and stuff. You have to add some bits so that there's some way for you can use ptrace to say, okay, what is the list of all the processes, the threads, where are they, what's their status, kind of thing. And you also need to do that using that single threading. You have to be able to stop all of them. So once you can leverage your single threading, it's actually a bit easier. But there's lots of little icky pieces of, okay, what is the right state? And when I do want to restart one, what do I do? There's an interesting little gotcha here, which you might not catch. Reparenting. What happens if you reparent your own parent? Your process tree is no longer a directed acyclic graph. It now has a loop. Do you remember how I mentioned how setpgid had a call where it walked up the process tree until it reached init? Guess what you can put your kernel in a loop on? Last I checked, this actually affected everyone, including Mac. So we actually did put a check into our ptrace code. I sent a note to some security mailing list, but so there's some other changes we need to make to our Syscall API. Some things where originally they were fairly simple APIs. We decided, we used rfork to create a thread and things like that. We need to make them a little richer. The previous one, okay, we actually had an assembly stub which actually did the real rfork call, and then it did the fix up of the stack pointer because, well, that's the whole point is different thread has a different stack, and then invoked the start function for the thread. There's a catch there. What happens if you get a signal before you fix up the stack pointer? It gets the thread and runs it on the parent thread's stack. This is bad. And for some reason, it seems like functional language interpreters like to send a lot of signals to new threads, because it seemed that our ports of, I think it was the Haskell implementation, one of the other ones, really liked hitting this. So you can't do that. You need to close that hole. So what you instead want is you want the kernel to actually do the setting of the stack pointer register in the new thread when it creates it. Of course, rfork doesn't actually have any place for you to put that. So we ended up coming with a new system call called a tfork, the thread fork. Takes a structure which has among it the stack. There you have to deal with all the machine-dependent work in the kernel. I really didn't want to know that much about the HPPA stack frame. And then you have to, you still need the ASM wrapper in Userspace. The problem is that you're still doing a call, so you still need a stack frame for that call, so you have to do the shifting, blah, blah. Okay. The other thing you really want is you want a per thread errno. It's required. And if you don't, eventually you will have XMMS die because it claims that a X call failed with error 0, which basically was a case of, it was a non-blocking call, and it got ewould block, and the errno got overwritten, which is annoying. So you need some way to have this per thread thing. You also want, it makes it useful to be to have some way to get a fast way to find out what your current thread's pthread T structure is. There's lots of useful information there that you'll want. So there's actually, the ELF people actually have an ABI that they've defined for many platforms for per thread storage class, so that you can actually define stuff which is per thread, and want to be able to leverage that at some point. So what we have is a kernel value, which is per thread, which the user space can request. And so you can set it with set TCB. That's the address of your thread control block. Kernel doesn't actually care where it points, but it just gives you, it'll let you set it and retrieve it. And you need to pass that in on your rfork call so that the thread starts out with this correct value. Because once again, you don't want any windows where if you got a signal, you'd have the wrong TCB value. You need AeroNode to work correctly inside signal handlers too. So have to have that set for you by the kernel. So what this actually ends up looking like, this is the kind of what it would look, the actual structures end up looking like. CR27, I believe that's HPPA. On HPPA, CR27, register 27 is reserved as the pointer to your thread control block. So for the initial thread, your thread control block, it's just a couple words. The first one, DTV, that's actually for the ELF ABI. It's going to point to something later on for implementing the thread local storage. We don't support that yet. We're getting there. But the other important thing is that it's a pointer to the thread structure, and then you can have in the thread structure a pointer to your actual AeroNode. You then have to have a override for the AeroNode under AeroNode function so that it actually knows, okay, dereference all this. Not too hard. There's other platforms define things slightly different. There's two different ABIs defined by ELF. This is, for instance, AMD64. Your %FS segment register points directly to your TCB. And there we cheated a little, and we actually put the AeroNode pointer into the TCB itself. So it's just saves one pointer chase for there. There's room. Now we do map this to whatever the ELF ABI defines where we can, i36%GS, so on. There's a couple which there are definitions for how to do this. We just haven't gone around to actually doing the MD work so that you can actually set this up. What this means, however, is that the get TCB function that I mentioned is very rarely used. On the platforms like on Spark, for instance, instead of calling that function, you just look at the register. The register points to my TCB. Woohoo! Off I go. AeroNode is fast. It's just on platforms like Alpha and ARM right now where we still have to, every time you actually do anything with AeroNode, it actually makes another system call. So, not the best. We'll make it faster. Now note this is only done in the thread library. libc, the libc base definitions for all this stuff don't do that. They can just use the static binding itself. So it's not a problem there. Then a little bit of fun stuff in the thread library to actually set up all those pointers when you finally actually open the thread library. We had to make some tweaks to our thread, the sleep wake up functions as well. It's very simple. You can see the original implementations from TED stuff. You have an identifier that's just a synchronization address, basically. The kernel, when someone sleeps on one address, the third wake up just looks for the same address somewhere by another call and wakes it up. The timeout was relative. Well, we really, it was kind of like poll, it was milliseconds kind of thing, but we really want it to actually be an absolute timeout, because it turns out all the timeouts in the pthread standard are absolute timeouts, where you actually specify this point in time of the clock. 1,500,000,000 seconds is when I want to wake up. So we changed it to actually pass in a struct time spec and then a clock ID. So the clock ID, for those who don't know, is that there's actually, POSIX defines a number of different clocks. There's the real-time clock, which is, seconds since 1970. There's a monotonic clock, which is usually something like second since boot, in effect, or something like that. But it's a clock that never gets shifted. And there's others that are possible. So this is just a way we can say, okay, which clock are you measuring from? Cancellation, just sorry for the record, I hate cancellation. Anyone here like it? Okay, sorry. Cancellation, thread cancellation is a way to say, okay, that thread over there, I want you to, I'm done with whatever you're doing. You're no longer useful to me. I'm firing you. You send it, basically it's, in effect, it's modeled after signals. Where there's certain points, what are called cancellation points, where the process is expected to say, oh, look, I was canceled, I'm going to die. The tricky bits are that one of the cancellation points is defined as pthread cond wait, conditional variable wait. And there's a requirement in the spec that says, okay, if you are interrupted, if you're canceled and you are waiting on a conditional variable, then you have to grab the mutex again before you exit. So you always, you come out of it with the mutex variable again. So there you have to do this a little extra cleanup processing. And it makes it so you have to be very careful in arranging exactly what state you're in. So in order to actually do this correctly, not have hangs, what we added is yet another argument, to thrsleep, where there's a way to say, look, I know you're trying to go to sleep, but if this value has been set, this flag variable, then act like you were interrupted. It's a way to close the race condition between a signal coming before and coming after the sleep has started. One of the fun things we did on OpenBSD is some years ago is that the write exclusive or execute bits, where normally in OpenBSD, no segment of memory in a process is both writable and executable. Makes it a lot harder for someone to come in and like overwrite your code segment with some cool garbage. For i386, for most platforms, this is really easy because their MMU actually has the ability to say, okay, these pages are read only and these pages are execute only. But i386, the ability to say which pages are not executable is pretty limited. You have to set the code segment limit, and it's kind of annoying. So in order to do that, what was done back in 2003, was that a shared library on i386 is actually two pieces. There's the code segment, and then there's the data segment, and they're mapped exactly a set distance apart, 1 gigabyte apart. And actually, the bindings inside them anticipate this. So they need to be placed that distance apart. So LDSO, when you tell it to map in a shared library, it says, okay, I need to put the code of this, I need to find some place I can put the code segment. So ask the kernel to give it a location. And then it says, now try putting the data segment above it, the right distance. And it uses, we added a system called mquery, which is like mmap, except it doesn't actually do the mapping. It just says, could the mapping take place? So it goes through, and for each of the segments, it tries and see if it can find a base. Oh wait, there was a conflict. Okay, move this guy up and try again, so on. Okay, it worked. Okay, well, there's a time of check, the time of use race there. mquery doesn't actually reserve the address that you did initially. So what if I say, okay, look, I can put the code down here. Let's go put something up here. And then something else one of your other thread comes in and maps over the bottom area. LDSO will then smack on top of it, and you'll actually end up with mappings put over where you thought they should be. Things would not be mapped the way you want them to be. That's bad. So what we needed is kind of the mmap equivalent of O-exclusive. So as O-create is to O-exclusive, we need map fixed is to, there isn't any. So we added map no replace, which is basically a way to say, okay, I'm going to map at this, if you can map at this fixed address, do so. If you can't, don't overwrite it, just fail. If you don't use map fixed, then the kernel would try picking another address, but we can't use that other address. It's not the right distance apart. So it says, okay, back it out. We can then back out all the mappings we actually already did, and then try again with a new place. We actually almost had it so that we could just get rid of mquery. I mean, really, is this useful? I mean, it's not. It creates this whole time of check, time of use problem. But it turns out that the fact that it doesn't actually make the page table changes is actually a big savings in time. If you've seen a lot of conflicts, if it has to do a lot of retries, then actually just trying without actually making the page table changes can really save a lot of computation. because every page table change is probably a TLB flush. It gets expensive. So we go ahead and it first tries with mquery, and then it says, okay, this looks good. Let's try it with this in a way that's safe. Userspace test bits. The ports people, God bless them. I hate you all. They found all the problems that we didn't anticipate, and then some ones we did. Like, for instance, yes, people actually do put things like DL close into their shared library FINI sections. I think they're insane, but they do it. And unfortunately, everyone else supports it, so we have to do it as well. So that means the lock you put around the DL open, DL close functions has to be recursive, because you do need to be able to do a DL close from inside a DL close. Not all operating systems punish people who do things like unlocking unlocked mutexes or locking your own mutex. Not everyone does that. We were really strict, and we've had to back off from that. There's some really broken code out there which gets away with it because no one else tries to call them on it. It's a shame. We actually do have our default is still more stringent than is required, but there's only so much pushing you can do from just a ports group. And they're the ones who actually end up doing the pushing because I'm banging on this stuff. Our mutex and conditional variable implementation originally was based on semaphores. And you can do this. Basically, the conditional wait is a down, conditional signal is an up if anyone's blocked, and then broadcast you have to count off and send them ups. But there's a bug in that. Well, okay, first of all, it's inefficient. For those who don't know, when you do when someone's doing the conditional wait, when they get woken up, they reacquire the mutex. This means that if you do a broadcast, suddenly all the threads are now blocking on the mutex. And if they all have to actually wake up, move over to the other queue, then you thrash all your caches as all these, it's 100 threads all wake up and do this. It's a kind of a thundering herd kind of problem. So what you can do this more efficiently by actually just having the broadcast operation. Okay, look, these guys are asleep. While they're asleep, let's just quietly move them over to the other queue, put them there, and then wake one up. And it can go off and actually grab the mutex. The bigger problem, however, is that semaphore implementation isn't actually safe. What can happen is, okay, you have one thread up there that blocks on the conditional variable. Okay, so it's kind of doing a semaphore down. And then some other thread comes in and says, okay, let's signal it, does an up. And then before that first thread can actually get around to waking up and grabbing the semaphore, have the second thread do another down on it. In effect, you can have a thread catch its own signal that it sent. Now this sounds like a really dumb thing to have this actually hurt. I mean, why is your design such a problem? Threads that are on a conditional variable, you shouldn't be waiting on the conditional variable if you just signaled on it, blah, blah, blah. You can get an argument to the design, but actually POSIX actually specifies that no, conditional signal can only wake up threads that must wake up at least one thread which is blocked at the time of the signal. And this implementation did not do that. You could lose a wake up in effect. So we had to change that. And programs do depend on that behavior. We actually just moved all the wait queues into Userspace. We actually have explicit queues now in Userspace where every mutex has a list of, okay, here's all the threads that are waiting for me, and then when someone needs to wake up, it just grabs the next one off, wakes up, and goes on. This conditional variable signal and broadcast operations can now transfer threads wholesale between the queues. It's a bit complicated. And I don't see a direct way to actually make this work with process shared. We're probably gonna have to actually follow what the FreeBSD guys did and actually have specific system calls for handling this stuff when we go on to do process shared. And you actually can kind of do priority inheritance, which I've now misspelled, I guess. But it's better than before, and it doesn't have that particular bug, which was actually causing a bunch of headaches. Interestingly enough, this bug is, there was just 2 weeks ago, there was a posting onto the Austin Group mailing list, which is the standardization group that keeps shepherding POSIX forward, where someone says, What does a shepherd do? Yes, what does a shepherd do with a sheep at the end of the season? Someone saying, glibc has the same problem. The GNU people apparently actually ended up driving into this exact same rat hole, and with their Mutex implementation, actually managed to get it so that it can lose wakeups and have a thread catch its own wakeup. So there's now been a tighter wording of the standards saying, no, really, don't do that. So there was some other missing stuff. One of the nice things, I mentioned how Sleep now has that clock ID thing that's actually exported all the way to user space, to the application level. With conditional variables, you can actually say wait until a point in time. So this lets you also say, okay, wait until this point in time on that clock. Useful if you have lots of problems with NTPD moving your clock around or something. Finally implemented barriers, spin locks. The cancellation stuff is a lot of wrappers. I just quietly copied the FreeBSD code, filed the copyright off. No, David, just kidding. Still not done. There's stuff to do. The pending signal set. These are the signals that are not yet delivered, but that have been sent to this process. Right now, we just have one per thread, which is correct. You're supposed to have one per thread. We also need to have one that's process-wide, so that threads, so that you can have a signal that if it hasn't decided what thread then can end up taking it, it can actually be pending for all of them. We actually mapped that on top of the initial threads pending set. And that does mean that there's some cases where you can have a thread get a signal that it shouldn't have actually gotten. pthread kill is not entirely reliable as a result. But it turns out it doesn't happen that often. I'm going to fix it. Sorry. Yes. We want to make things faster, of course. Big lock, yes. We still, most everything in the kernel in OpenBSD is still big lock. Kirk, you're actually, I'm going to steal your notes for your talk later. Well, that's a nice Mac. Yeah, okay. A couple of the other guys, Hasbert is working on the schedule lock, making it less contended. ptrace, I mentioned there's some issues there. And we've already got some stuff working forward towards being able to do process shared mutexes, where you need the identifier that inside the kernel that you're matching on has to be associated with, if you have shared memory between two different processes, so they both have some shared memory segment, the address of that shared memory segment can be different in the two. So you have to kind of transform those addresses into a real unique identifier inside the kernel so you can match them up when you want to identify someone else's mutex, a mutex that's in the shared memory, for instance. So we actually got some work going on that already, preliminary implementation of the necessary bits there. Of course, MD bits for TLS and alpha, and really would like to get some of these other wacky stuff. One cool thing is that okay, on OpenBSD, our GOT and PLT, the technical stuff from ELF standard, these are the indirection tables that are used for linking. These are made read-only most of the time. They're only made read-write when LDSO actually needs to update a binding inside one of these. So normally when the shared library first goes, these are actually, all the GOT entries all point to an address inside LDSO, and then when you actually try to use a symbol, LDSO says, oh, hey, you went past this, and it puts the real address in place. Well, in order to do that, we actually have to do quite a bit of work. You have to block signals because we need to do this. The key thing is we have to do this memory protection bits. Well, because there's no reference counting on how many times you've made something read-write, read-only, we need to make sure you don't re-enter this particular chunk of code. So we have to block all signals so we can't get interrupted and come back around through and binding again. And we also have to make sure that another thread doesn't do the same thing. So suddenly, just a simple, update this lazy entry, suddenly turns into two more system calls and a spin lock if you have the threads library loaded. And mprotect often involves TLB flushes because you have to go thrash the page tables a few times. And for short-lived processes, yes, almost all, most of your system calls may be these lazy binding resolutions. Ktrace can look kind of embarrassing at times, in fact. Fortunately, these are relatively fast system calls. Well, at least the sig proc mask is. mprotect isn't, unfortunately. But that's annoying. So what if we actually just had a system call which could take care of all the atomicity guarantees, and because it's in the kernel, it can actually cheat and update the address, some of the mappings behind your back. You don't have to flush all the TLBs. You do have to flush some of the caches. You do have to let other CPUs know so they don't have bad cache versions of the page that's being updated. But you can pull off some optimizations there. So this was one idea. The idea is that you'd actually tell the kernel also, yes, I know this area is read-only, just do it anyway. There's some tricks. Okay, PowerPC, you actually have to write a couple different things, so suddenly the system call starts growing more arguments and getting more complicated. And it's, if you're on Spark, you have to write the bytes in backwards order and call isync between each, man. And then, okay, is this just going to turn into a problem? Because look, isn't this the first thing an attacker's going to try to use? Because hey, look, I can write over a read-only page. Woohoo! So maybe we still have to work out how can we prevent this from being that sort of a problem? Can we lock it into LDSO some way? Tell the kernel ahead of time only this call? Well, return-oriented programming is I don't know how many people here know what ROP is, return-oriented programming. Basically, it's a attack method where instead of calling into libc to do something, you set up a stack which says, I'm going to return into a libc function, the middle of a libc function, which happens to do the right operations and then do a return. And on platforms like i386, this may involve returning into the middle of an instruction, which when decoded on the non-anticipated instruction boundary looks like the right instructions. Now this seems okay, really could this work? Okay, here's how far it's gone. There's some guys who came up with a compiler for compiling Spark, okay, so fixed instruction size, Spark on Solaris, return-oriented programs. So they have a Turing machine built on top of gadgets stuffed in libc. So, and this involves no writing over of text or anything. All you have to do is be able to write over someone's stack. If you can write over someone's stack, you can run a Turing machine. Yeah, so if they could return into LDSO and hit this, then they could do whatever they wanted at that point. So finding some way to actually protect this would be necessary before we actually try making this real. Other things we'd really like thread local storage. With the bits of the TCP stuff, we have most of we have the kernel bits basically. What's not there is bin utils and GCC. Okay, the bin utils we have is an older bin utils. They changed the license in an annoying way. And it was never fully implemented for at least a couple for HPPA, I think, and Spark actually, they might not have, the GNU bin utils might not have actually got that one done. So we'd have to update that, but there is some stuff that now really wants to use it. You can't DL open, some other annoying things. Oh yeah, we want to fix some bugs, I hear, or something. And the annoying thing of there's a big lock in libc around the resolver, which means that, for instance, in Mozilla, if you have a slow, there's some DNS resolver out there which is slow, it often, oh look, I can't resolve any web pages. Okay, so we're working on an async resolver so that different threads don't have a problem. Any questions? It's either very good or very bad. SB.
For that part about not being able to develop any vector through unresolved functions, could you put something inside that you get back to lazy binding for a specific function?
You have to go. That's basically what the introduction to the jump table does. Is you basically move out of LDSO the relocations. LDSO, I guess you could try to hack into LDSO a way to say flush a set of relocations. The problem is, could you be in the middle of one of those calls, and what's going to happen when you try to return back out of that? So it's I guess it's probably possible, but it's the known method is to go ahead and use the jump table. That's what Solaris, FreeBSD, I think probably NetBSD probably did that too. So that's a known method, and everyone knows it works. So we probably just do the same thing rather than trying to. I don't think trying to teach LDSO is the benefit for doing it for other things is probably pretty. If no one else does it, then no one's going to take advantage of it. If we took advantage, okay, we'll see.
So when you're trying to reparent your parent, does not allow that to happen?
Correct. The Sys now actually has a call to inferiors itself to say, oh, am I trying to recall this on one of my own parents? If so, ban it. The one exception is if you are in permanently insecure mode, then you can do init. Because otherwise there'd be no way to ever ptrace init. And so someone could probably come up with a useful case for doing that. So I said, okay, if you're permanently insecure, the check is turned off. But yeah, no. Otherwise, no parenting your parent. No reparenting your parent. Anyone else? Last calls. Out of here.